So originally, I've deviated from the abstract a little bit because some of the theories are not there. So what I'm going to talk about is going to tell you about new approaches for deep learning in MR, and then also tell you a little bit of theory for feature learning via gradient descent. But at the end, I'm going to try to connect the two a little bit to see how these kinds of theories could actually apply for inverse problems. Okay, so that's the plan. But before I do that, let me just, because I'm going to talk about a very specific MR problem, let me motivate the general area a little bit at a more higher level. So this MR problem that I'm going to talk about, in my view, is just one of the simple examples of AI for sciences. And of course, different people mean different things by AI for the sciences. What we focus on is the following, which is imagine, basically in the sciences, you often have some sort of measurement apparatus, right? If you're not happy with the quality of your measurements, right, what you typically do is you actually go and buy a more expensive equipment, right? You buy like a fancier telescope, like a larger microscope, and so on, right? And this is how you get that higher quality signal or image. Now, there is a lot of promise for using AI in this field is that maybe you can actually use your low quality images or measurements, but augmented with powerful kind of AI ML algorithms to actually reconstruct the higher quality measurements from this, right? So that's like the promise. And so obviously there's a lot of promise in doing techniques like this. You could really gain a lot by this. But there's also a lot of challenges, right, in this area. So one of them is like the reliability challenge. And so here's a cool example, right, where you could actually potentially hallucinate. When you do MR reconstruction, you could actually hallucinate details, which is actually diagnostically significant, but it's not there, okay? So definitely you have this issue. You could have critical reconstruction errors, right? So in this case, this is a nanoscale imaging application where you could actually see like a chip there where it's not, right? It's actually a critical mistake. So that's kind of what the reliability is a challenge in this field. Another issue is bias. This is actually a Twitter famous image, which is like, it's a super resolution application where you're trying to super resolve this picture of Obama, right? Using kind of a super resolution scheme. But when you super resolve it, it actually becomes white, right? So there's a lot of bias that you also need to tackle. So that's one challenge. And then finally, like maybe a really important challenge is that you have a data scarcity challenge in the sense that if you look at a lot of the modern neural networks that work well, they typically work well for applications in like, I would say, internet-like applications where data is available on the internet. This is like whether you look at computer vision or NLP. So in this kind of cases, data acquisition is easy because you take data off of the internet. And the cost of gathering data is fairly low, and at least labeling it. And finally, you have lots and lots of data because it is the internet. But how about scientific data? So if you look at the scientific pipeline, so you have some sort of phenomenon that you're trying to measure, you have some sort of sensing, so you get a data point, you gather different data points, and then finally you have your algorithm. So if you look at all three parts of this pipeline in scientific domain, there's challenges, right? The acquisition could be very slow or costly, unlike internet data. The data set collection, again, is costly. It could be actually harmful, right? If it's a medical domain, it might be harmful to the human. Sometimes the image gets destructed, or the sample gets destructed when you image it. And finally, the knowledge extraction is also more difficult because the data that you're dealing with is typically more complicated. So all parts of this pipeline is much more heavy. And again, like a particular example, if you look at some of the medical domain, data acquisition could be slow and or harmful. The cost can be very high. Like stuff like MR machines are not cheap. And then unlike internet where there's lots of data available, you have very small, limited public data sets, right? So this is yet another kind of challenge. And then finally, this is less of an issue, but there's also a computational complexity challenge in the sense that actually like scientific data is actually higher, even higher dimensional, right? So if you look at even imaging, right, the data is of much higher spatial resolution. There's more challenge, the channels, there's sometimes this complex valued and so on. So even the nature of the data sets are typically larger, right? At least the individual data, even though we don't have that many data points. So these are kind of issues that we have to be aware of. And so before I jump to the specific of the MR, I have to say, like, again, AI for science is a very active field. There's a lot of exciting things happening. Both in computational imaging, there's really a lot of cool stuff happening. And even in the basic sciences over the past 5 years, there's really a lot of exciting stuff. The focus of this talk will be very narrow. At the first part will be on just doing deep learning for inverse problems and medical imaging in particular. But the wider discipline, there's a lot of exciting things happening, which I'm not going to talk about. So with that, I'm just going to focus on this specific problem of MR reconstruction and tell you briefly how we can maybe address some of the issues that I mentioned very quickly. So, and in particular, this part of the talk is joint work with Zalan Fabian and Berk Tinaz, both are students at USC. So the MR reconstruction pipeline is actually very simple. So what you get to see, if you want to image something, what you get to see is samples from the Fourier domain, right? So at least the toy model is, you have Fourier transform plus undersampling plus noise, and the question is, how do you go from the measurements to actually the image, right? So this is the question. Well, in reality, the pipeline is actually a little bit more complicated than that, because what you have is like the body part that you're trying to image. Then there are certain coil sensitivity maps, because typically you have multiple coils. So then you do the Fourier transform, there's noise, and then you undersample, right? So that's the more practical pipeline these days. So you get measurements of this form. And then you're trying to reconstruct. Classically, what you would do is like kind of the compressed sensing reconstruction scheme is that you say, okay, I have two terms. You have a data consistency term. You make sure the model is consistent with your measurements. And then you have some sort of regularizer, which is supposed to capture prior knowledge about the signal, right? So that's how classically things work. But these days, at least the approach that seems to be dominant, and we will talk about this, is to just do end-to-end deep learning reconstruction, which is just you gather a bunch of training data consistent of the input images and the corresponding measurements. And from these, you just want to find a network that directly goes from measurement space to the image, right? So it's just based on training samples. So this is often called end-to-end reconstruction in this area. So luckily for MR reconstructions, there is actually a very nice large public data set available. This is a joint effort by Facebook and NYU. And this is a pretty rich data set. It has, at this point, it has multiple body parts, different scanners, It's a pretty rich data set. And if you look at like the leaderboard at least 2 years ago, you see all of these approaches are based on a certain technique, which is end-to-end deep networks, right? So that's why I'm going to focus on that. And you can notice that over the past 2 years, essentially the top performers have not changed. So it seems like the results have saturated a little bit. I'm excluding one team from here. It's because it's from a private company and then they don't make their code publicly available. But that's essentially the status of the field. So all of these networks happen to be based on unrolled methods. So let me tell you a little bit what they are. So remember like the classical compressed sensing inverse problem formulation. So unrolled methods kind of are based on that in the sense that now, if you try to use an iterative algorithm to solve this kind of problem, well, what would happen is you would have kind of two terms, right? You have the gradient of the first term, and then you have the gradient of the regularizer. But of course, the critical question is, what regularizer do I use, right? Because we don't know, right? What is the good regularizer? So the idea behind end-to-end methods is actually to say, instead of trying to answer this question, is like, I'm just going to replace the gradient of the regularizer with basically some neural network, right? So you parameterize the regularizer gradient by a neural network. And this actually also connects very well to the talk Yi gave yesterday. So then the pipeline becomes, I have a data consistency term. I have like kind of a neural network to model the gradient of the regularizer, and I just repeat this, right? So I repeat this pipeline multiple times. And then, on the training data, I just train all of the parameters of all of these networks, right? And then at reconstruction time, I just use this network to directly reconstruct. And so these are the end-to-end methods that work very well in practice. And in particular, the end-to-end methods that work well, there's some other tricks, is often you have to do this unrolling in the Fourier domain. So that's one trick that it actually turns out to be important. So you have to unroll in the Fourier domain. And of course, the entire pipeline is a little bit more complicated because you have, again, multiple coils. So you have to kind of contract them to a single image. Then you apply the neural network, and then you go back. And the coil sensitivities themselves are also typically, basically found out based on data, learned from the data. And you have like a smaller network. This is a shape matrix estimation network to actually even find the coil sensitivities. So this is kind of the entire pipeline for end-to-end training for MR these days. And the typical denoisers that are used are kind of these UNet architectures, which have kind of a multi-scale feel to them. These are the networks that seem to work very well, in particular in the state-of-the-art E2 E-VARNet model that was the top performer. And so the question we asked was, given like the excitement about transformers, is like, can we do better with like modern architectures, in particular with transformer models, right? And so this is like a story of how we went about coming up with the right transformer network for this domain. And so this is the network we come up with, which we called HummusNet. It's very appropriate in the Middle East to use that, right? Even though as I'm Persian, we do not have hummus, but we were going to steal that concept. Okay, so let me tell you the different components. So first of all, let me also tell you why do we think transformers are good in this context, right? So there are two benefits of transformers that I think makes them particularly well suited to this case, which is, first of all, the convolution kernels are content independent, right? So convolution kernels are content independent in the sense that, whether it's a bone or some other structure, they don't care. And second, convolutional networks are not very good at capturing long-range dependencies, right? So you could have a piece of bone on one side of the image and a piece of bone on a completely different side of the image. And obviously, convolutions, at least shallow ones, would not be able to capture that very effectively. And so, transformers are known to be better at doing this. So there is hope that in this context, they would also work well through like the self-attention mechanism. The details of the self-attention mechanism are not too important. This is how it works. The issue that we are going to have to face with is that this self-attention model, unfortunately, is quadratic in the number of patches. And so this is going to be a problem for us. So that is something we will have to contend with. And so one way of dealing with that is kind of becoming well established in the literature is you kind of use local window attention. So you calculate these dot products only in blocks, and then you change the patterns of blocks between the different settings. And so this is where you get these kind of swine transformers, right? Which are known to work for some reconstruction problems, for example, for super resolution. So they end up being like a convolutional transformer hybrid, which actually seems to be working well in all sorts of different domains. So then they kind of have the benefit of long-range dependencies coming from the self-attention mechanism. They have the implicit bias of the convolutional networks, and they kind of do single-scale processing. So they're really good for this context.
But when we tried this kind of swine transformer, so you know, remember for the gradient of the regularizer, for the denoiser, you could just now plug in maybe one of these swine transformer models. So if you do this and you pick the largest ones that fit into your GPU memory, because that's usually the constraints that you have, it actually does not work that well. So if you use an unrolled swine transformer and you pick the largest ones that fit into the GPU, it will actually, the performance will degrade significantly. And by the way, this is the SSIM score. It's very sensitive. So it's actually 1% drop is actually quite significant. So it really does not work that well. And so we have to figure out a way to fix this. And so there's, the issue here is that, you know, one fix we realize is that, well, these swine transformers are not multi-scale in nature. We know in a lot of signal processing applications, we know wavelets work well. You know, multi-scale is very good in signal processing. And in particular, the UNet model that I mentioned, right, is somehow multi-scale, the existing models. So the first idea, which is simple, is like we were going to try to make swine transformers multi-scale in nature. And so we do a bunch of downsampling and upsampling to achieve this, and so you end up with a multi-scale hybrid feature extractor. So if you now use this and pick the largest one that fits into GPU, you get you know, much better numbers, but you're still not there. Okay, so you're kind of getting close to the state of the art already by doing this idea. So then to go further, we have to somehow fix this memory issue, right? To do this. So it turns out that the reason memory is such a bottleneck, particularly in these problems, is that, you know, so for image reconstruction tasks, the input images are of much higher resolution, and the prediction task is also much denser, right? So if you look at the classification pipeline, you could have fairly large image patches. So this is how a vision transformer would work. So you have these image patches, you get token embeddings out of that, and then you pass it through the vision transformer. And then finally, you get the classification, in this case, like an African elephant. But if you look at if you do the same thing for MR reconstruction, it turns out because you have such high spatial resolution, you actually have to pick much smaller patches. In particular, we had to pick patches of size 1, and in a moment, I'll tell you, you cannot pick anything larger. So, and that means that the token embedding is much, much higher. And so this is what is causing the memory bottleneck. You know, one reason these token embeddings have to be large for the network to work well is because, you know, your prediction task is not just a single classification, it's an entire image, right? So naturally, these token embeddings have to be of much higher dimension. And so these are the reason we hit this memory bottleneck. So now, to fix this, so the idea is simple. And just before I tell you how we fix it, if you use larger patch sizes, it will not work. So if you go by 2 by 2 pixels, right, the performance will drop significantly again. So you really need very small patches for this idea to work. And so the fix we have is kind of what we do is we extract higher resolution features via convolution, and we pass those through the transformer network, and then we combine them again using another convolutional layer. So that's kind of the approach. And we also wrap it, as is, I think, somewhat typical in this area, in a residual network. And so this is how we get the denoiser block for our network. So this is kind of homogeneous in its entirety. And then to achieve further improvements, we use 2 common tricks, which is very common in this area. We add unrolling, as I discussed. So this is, everybody does this. And another idea is like this idea of adjacent slice reconstruction, which is also very important. Instead of doing reconstruction based on just a single image, you do it based on 3 adjacent images. And then you just use this to reconstruct just the middle image. So it turns out this is also important. So we also use this trick. So if you combine all of these tricks, so then you know, we finally get our result. So this is like the, you know, state of the art. We can kind of slightly improve on it. Again, the numbers don't look much higher, but again, this measure of accuracy is quite sensitive, right? So again, if you look at the the top of the leaderboard, you'll realize this. We tried it on different data set. We tried it on FastMR. We tried it on the Stanford PD data set. So we observe improvements across data sets. And, so we kind of beat the state of the art. And again, you can see the numbers are at the top are all very close to each other. Right? So this sensitivity measure is this measure of accuracy is very sensitive. Okay, so that's our results. So here are some images of reconstruction. You can see, like, compared to the ground truth, we actually get, this is actually very good because this screen is the only screen you can see all the fine details. So you can get very high quality images. And, but of course, like, the reason we're interested in using transformers is not to get, like, this minor improvements in performance accuracy, even though we were happy about that. The real reason is to tackle some of the other issues that I talked about earlier, right? For example, how do you reduce reliance on the training data, right? And, actually, it actually drops very significantly if you use much less training data. So here's a picture where on the x-axis, I show you the amount of training data the algorithm sees versus this SSIM score. And you actually see a significant drop as you use less and less training data. So like that's the baseline in blue. If you use some kind of data augmentation techniques, this is stuff we worked out with Reinhard in the audience, you actually can improve this curve a little bit. And so if you end up using some contrastive methods, you can do even better. But the hope is that using transformer models, you could do much better. I mean, we're not there yet. So Hammersnet is at this right corner, right? But transformer models combined with some of the data reduction techniques seem to be very good. So we're very optimistic that we could get much better results. And then the dream really is that, you get basically the same performance of the state of the art using only 1% of the training data, right? And again, because these numbers look so close, there is actually a lot of difference in image quality, even with 1% difference, right? So this is actually, this drop in performance is somewhat significant. So that's one issue that hopefully these transformer models are better at fixing. And I do want to mention briefly that if you actually can make the network learn with less training data, it also has all of the other benefits that I discussed, surprisingly. It actually improves robustness and reliability. So for example, these are the experiments that show, like, it improves robustness to unseen scanners, even unseen anatomies, going from knee to brain and vice versa. And it even also removes some of the hallucination artifacts. So actually, if you train the network to learn with less data, surprisingly, it actually removes some of the hallucinations, right? Because, it avoids overfitting to the data too much. So that is like kind of a side benefit. And then the real dream, the real reason that I got into this area is, like, how could we achieve a high performance low field MR? So this is still very much work in progress, but here the idea is that can we actually do reliable reconstruction with low field scanners, which operate at a much lower magnetic field? Why is that good? Because it means that you could use much smaller coils, right? So instead of, like, the MR machine being like an entire room, it could be potentially even portable, right? So it would be much lower cost. It also reduces susceptibility to a lot of artifacts, right? For example, in normal MR machines, you cannot have pacemakers, right? Patients have pacemakers. If you can actually go to lower magnetic fields, you can use, patients could have pacemakers and so on. But that's the advantages of doing this. But there's also a lot of cons. When you have, like, operate at a lower Tesla, lower magnetic field, you get much lower SNR, right? Because it is much noisier. And then also, because you have very few scanners of this kind, there's actually very limited data of this kind. In fact, in the US, there's only 3 high-performance low-field scanners, right? USC happens to have one of them, so that's why we got into this. But basically, so So this issue of data is even more prominent in these applications. So that's kind of the dream for this area. So even though I focused on a very specific pipeline, right, the hope is that we can eventually get to these more complicated pipelines. This is actually work in progress. We're gathering the data. We're trying to go there. Okay, so, and I want to zoom out a little bit and remind you that, you know, this is just one instance of AI for the sciences. There's a lot of more exciting applications, right? I'm actually fortunate to talk a lot of basic scientists through this Packard Fellows Network almost every year. It's really incredibly exciting what people are actually doing in the basic sciences these days. So I think there's a lot of exciting things happening. Okay, so that's kind of the first part of the talk. In the second part, you know, I want to try to eventually explain like the performance of these end-to-end networks, but we're still not there yet. So I'll talk about feature learning via gradient descent more generally for a simple problem, which is low-rank reconstruction, and then I'll come back and tell you how it impacts like a simple formulation of these reconstruction problems, okay? So let me briefly motivate why we need kind of theoretical foundations in this area, in particular, given all of the exciting theory that has happened over the past few years. So the basic issue is, and I think Yi actually mentioned this very well, we have a lot of theoretical foundations, but you know, there's a lot of limitations with it. So in some sense, the foundations are still a little bit shaky, right? They're not very predictive and so on, right? And so, you know, we're going to focus on fixing one small aspect of this, which has to do with feature learning, and I'll tell you about this. And so why is it that we need these stronger foundations? There's kind of two high-level issues. One is that basically, you know, existing theoretical results, it's really incapable of even explaining a lot of contemporary practices, right? So for example, you know, choice of the architecture, you know, none of the theory really explains why you need fully connected versus convolutional or a transformer model. A lot of things having to do with normalization. You know, a lot of things having to do with representation learning in general, although there's a lot of cool work by people in the audience, and we heard some this morning, right? But there's still a lot of mysteries associated with these modern practices. But I'm not going to focus on those. I'm actually going to focus on even toyer settings, right? There's even problems in very simple toy settings. And so really, like, current theory even fails us in very, very simple instances. And here's one good example. So imagine you have a bunch of, you just have a one hidden layer network, and you have a bunch of data points in 3D, and you just want to fit, you know, this one hidden layer network to these data points, right? So this is what the existing theory, with the existing hyperparameters in theory, this is the kind of reconstruction you would get, or the function estimation that you get. If you actually use, like, you know, practical hyperparameters, you actually get much nicer, smoother surfaces. So the issue that I'm going to point out here is that basically existing theory operates with unrealistic hyperparameter choices, whether it's like very small step sizes, very wide networks, or very large initialization scale, right? And it may seem that this is not important, right, because it's just hyperparameters, but these are very rich function classes, and if we don't use the right hyperparameters, we actually may end up, you know, getting really erratic functions, right? And so existing theory does not apply in these practical regimes, right? And of course, so we will talk about building that stronger foundations. There's one key issue that we have to focus for that is this issue of overparameterization without overfitting. Modern neural networks contain a lot more parameters than training data, right? And you expect this overfitting to happen, but in practice what happens is that you get a very nice fit to the data. And there's kind of two mysteries associated with that. One has to do with optimization. This very simple example that a lot of you are familiar with captures that well. So imagine a very simple toy setting where your data is generated according to a planted neural network with 3 hidden nodes, and you train a model of the same size to fit to this data. So if you run gradient descent on this, you actually hit a local optimum, right? So in this very simple case. But if you over-parameterize in the sense that you add more hidden nodes, you actually all of a sudden get to the global optimum, right? So the first question is like, what is the impact of over-parameterization on the landscape that makes this happen, right? So how do you get global convergence analysis by this over-parameterization? So that's kind of the first challenge. The second one, which is arguably much more important, is that, okay, you over-parameterize, so you actually have many global optimum in the training loss now because you over-parameterize. So how do you know that the global optimum that you get actually has good prediction power, right? So the training loss maybe have a lot of global optimum, but from a test perspective, not all of them are created equal. In particular, for example, if you initialize somewhere, you get some test loss, right? If you initialize somewhere else, you actually get a different performance. And this, even though this is a toy picture, this is not a toy phenomena, which is like, even by just changing the scale of initialization, you actually get very different performance, right? You can get very different global optimum. And let me show you that to you more clearly, right? You can actually reach different global optimum by just changing the initialization scale. And by that, I mean the standard deviation of the random initialization, right? So here's, again, same simple one hidden layer neural network example. You're changing the scale of initialization. That's the only thing you're changing on the x-axis. And on the y-axis, the reconstruction. You can see for all initialization scales, you get 0 training error, very small training error. But the test error is dramatically different, right? So at large initialization, the test error is high. This is where existing theory actually operates. And at small initialization scale, it's much better. So this existing theory, which I'll talk about very briefly, is known as the NTK or the lazy regime or the linear regime, right? And essentially, in this regime, neural network essentially behave like kernel methods, right? So it allows you to develop some bounds on the performance of neural network, but it's not very good because, you know, the features are frozen to the one at initialization. So in practice, you can get actually much better bounds, right? And so this is in particular the mystery we're going to focus on is how do you establish generalization of vanilla gradient descent with small random initialization, not large, right? So let me tell you how this existing theory operates very briefly. I'm sure many of you are familiar with it, so I can go over this very quickly. So as a prelude, look at like a least squares problem in the over-parameterized case. So you have less training data than number of parameters. So n is actually less than p. So in this case, if you run gradient descent, it has like 3 cool properties. First of all, you get global convergence because it's actually convex here. You converge to the global optimum, which is closest to theta 0. And also the total gradient path is relatively short. Modulo condition number, you converge very quickly. So it turns out that you can really basically directly generalize this in the nonlinear case. So if you also have a nonlinear least squares problem now, and if you try to run gradient descent on this, then the gradient has this form, right, which is like Jacobian transpose. Jacobian is just the first order derivative of the output of the model times the residual. So essentially in this problem, the Jacobian kind of behaves like the x for the linear problem. And so it's as if you're working with these nonlinear features of the Jacobian, essentially. And so the way a lot of the existing theory works is under some technical assumptions on the Jacobian, which I'm not going to get into, you can show that along the trajectory of gradient descent, the function essentially stays linear, right? So that's kind of the formulation. And so you can also show that these technical conditions are satisfied when you have both like a sufficiently wide network and a large scale of initialization. And then obviously if you know that, if you can understand the trajectory, you can also get some optimization and generalization guarantees. But in this case, it would say that the generalization guarantees we get is as good as kind of the random features you use at initialization, right, of this Jacobian matrix. And so there's like a lot of theoretical results about this. We kind of did an argument like this using this linearization idea in a paper with Jason and Adil a few years ago. And then this kind of idea was, a lot of people worked on it, and it's like became really popular after these kind of NTK papers, including by a lot of people in the audience. So a lot of exciting things happened. But then, the fundamental issue is that, your features are frozen to that at initialization, and then this is not good. You don't get as good of a performance out of the network as you could, right? And this picture, I think this example kind of demonstrates that very well, this visualization. So for this visualization, what we're going to do, we're going to, and this kind of, I think the first people that did this is Bach and Chiza. So we're going to embed the hidden nodes as vector in higher dimension. So what do I mean by that? So again, we focus again on the simple one hidden layer model. So corresponding to each hidden node, we're going to look at the input vector followed by the absolute value of the output weights, right? So for each hidden node, you actually end up having like a point in higher dimension. And you see 3 black lines. These black lines are actually the directions of the planted model. Remember, like the original model generating the data is a one hidden layer network with 3 hidden nodes. The black lines are those directions. So in this kind of like non-lazy regime, this is where we don't have theory for, right? Where you start from small random initialization, something very interesting happens. All of those hidden nodes actually align themselves with one of those pre-planted models as you run gradient descent, right? Whereas, in this lazy or anti-K regime where we do have good theory for, you do get global optimality, but the features are essentially, the nodes don't move around too much, right? Because the features have to stay close to the one at initialization. And so you get much more erratic functions out of this, right? In some sense, you don't find the simple underlying model because you didn't learn the right features, right? And so this, I think this kind of depiction kind of demonstrates the issue very well. So in some sense, existing theory does not apply in these practical regimes, even for these toy models, right? And so this part of the talk is basically an effort to go beyond this lazy regime. And we've done this for 3 problems. So one is low-rank reconstruction. We've done it for one hidden layer networks. And very recently, we've looked at this for end-to-end training methods. So Jason is actually going to talk about the second one, I think tomorrow or Friday. So I will not talk about this, right? So I'll only talk about the first one and briefly mention how it would extend to the last problem, right? So I'm going to talk about low-rank reconstruction mainly for one hidden layer networks. You can come to Jason's talk, so it's a plug for him. So basically, for low-rank reconstruction, this is joint work with Dominic Stoger and Changzi Ji. Dominic is now a faculty in Germany. So low-rank reconstruction, which was talked about in the tutorials quite a bit. So here, what you're trying to do is, you have linear measurements from a low-rank matrix, right? And you're trying to reconstruct it, and let's say the underlying matrix has rank R star, right? So now, the way over-parameterization manifests itself in this problem is also very simple. You just fit a model of higher rank, right? Instead of rank R star, you just fit a model where it has rank R bigger than R star. So you just fit a higher rank. This is equivalent to adding more hidden nodes in your neural network model. So, and then you just run gradient descent, starting hopefully with small random initialization, right? So even in this problem, which is a much simpler problem than neural networks, arguably like these challenges exist. Of course, the non-convexity, the optimization challenge is there. So in the tutorial, people talked a lot about how to address this, right? There's kind of 2 techniques roughly to address the non-convexity here, including by a lot of people in the audience. Almost half of the audience have worked on some problem of this form. So one class of ideas is like you come up with a clever initialization technique using spectral methods, and then you kind of do a local convergence analysis, right? Which is like basically you come up with an initialization which is kind of close, and then you do a local convergence to get there, right? And then there's a second class of results. Again, talked a lot about a lot yesterday, which is like you kind of study the landscape, right? Figure out where the global optima are, where are the bad local optima, where are like the saddle points, and then you come up with clever algorithms to to avoid the bad regions. Trust region methods, again, there was an entire tutorial about that yesterday, right? So a lot of work by John Wright and his team, former team, who are all in the audience now. So then, but despite all of this progress, there's not a lot of work that actually just focuses on what happens if I just run gradient descent from small random initialization. Can I get actually rates of convergence to global optimum, right? So even in this kind of arguably much simpler problem, this is not completely understood. And of course, the generalization challenge is even more, more significant here, right? So again, we're working in this over-parameterized regime. So it means the number of parameters of the model is actually bigger than the number of samples, training data, which is also bigger than the true number of the parameters in the original problem, right? So we're operating in this regime. And in this regime, if you have a large initialization scale, if you have a large standard deviation at initialization, using this kind of NTK lazy style theory is actually not too hard to show that you can achieve global optimality, right? So this is something we proved a few years ago with a colleague at now Michigan, Samet Oimak. But the issue is that here, because you're over-parameterized, you have many global optimum. So the training, you can easily prove that the training loss is 0. But if you look at the test loss, which happens to be proportional to the error in reconstructing the underlying low-rank matrix, this can be actually potentially large when you have large scale of initialization. And interestingly enough, you get exactly the same curve as you got for neural networks, right? So for different training data, right, you get, for different initialization scale, you get 0 training error, but you get very different test performance. It's exactly the same plot. Again, like existing theory operates here, we want to focus on here, right? Which is, if you use small random initialization, how do I get gradient descent to converge and also generalize? So that's kind of the challenge. So it turns out there's a key idea that we use in the proofs. So before I tell you that in more technical detail, let me just tell you about the key idea. Roughly speaking, the idea is that gradient descent plus over-parameterization essentially behaves like running power method on certain matrices, right, or tensors in the case of neural networks. So again, I'll tell you what those matrices are, but here's a demonstration. So, in one case, I'm running gradient descent. In the other case, from small random initialization. In the other case, I'm just running power method on that fixed matrix, okay? So if you compare the trajectory, at least initially, they're the same. Eventually, they diverge, but initially, it's the same. Again, eventually they diverge. But this is good because it says that if I want to analyze the trajectory of gradient descent, I could just analyze power method on a fixed matrix, which is very easy to do, right? So that's the basic idea. And then, once I'm close, they diverge, but maybe I could do a local convergence analysis again. And so here's a slightly different picture that shows this, right? It shows the angle between the gradient descent and power method with the underlying matrix. You can see initially the trajectory is really on top of each other. So this is not just a theoretical construct. It really is true in practice. Now, the interesting part is that we're running power method on these certain matrices, equivalent to running power method on certain matrices. These are exactly the kind of this is exactly the initialization schemes we used to do to initialize these low-rank reconstruction problems 5-6 years ago when we worked on spectral initialization followed by gradient descent. So here what we're saying is that gradient descent from small random initialization actually automatically does spectral initialization, right? Which is very exciting, right? Because it connects to all of the previous literature that a lot of us worked on. So with that, here is our result. So for simplicity, I'm going to assume the measurements are Gaussian and the condition number of the problem is order 1. So we're going to assume this is over-parameterized, so rank R is bigger than R star. The training data that you see, this should be R star times the product, right? We need a little bit more. But then if you start from small random initialization, what you can show is that after a certain number of iterations, the generalization error actually behaves like this. The polynomial is not important. The point is that it goes to 0 with the initialization scale. So if you actually have a very small initialization scale, you get actually 0. Actually, compared to the previous versions of this result that some of the people of the audience have seen, like the dependence on alpha is much cleaner now. So that's kind of our result. So this actually does capture what we want. As alpha goes to 0, you basically get perfect reconstruction. So what happens in the last phase? Because you may ask, okay, we stop at a certain number of iterations. So you can show that this last phase doesn't affect the generalization performance. But interestingly enough, the convergence of the loss actually dramatically slows down. You no longer have a geometric convergence rate like you have in this phase. The training loss goes to 0, but at a rate that is polynomial, like 1 over t, right? Yeah, and in fact, in certain cases, you can still show that, you get a geometric convergence rate, but at a slower rate. And this is actually very much in the spirit of this result by René and his collaborators, where they show that in this regime, you actually can get geometric convergence rate. But it depends on the noise scale. It's not completely clear what is the best rate possible in this regime. So the last phase, there's still some stuff to be figured out. But let me make some comments about the results, right? So these kinds of Gaussian assumptions, you can relax them to the RIP. And in fact, even if the model is not overparameterized, when R is equal to R star, this is the only deterministic result that can show this. So previous results in the literature, including by some of the organizers, right? Are based on random measurement results that require leave one out analysis. Our result is purely deterministic. So in this sense, even for R equals R star, the results are kind of interesting. So there is another extreme case, which is heavily overparameterization. When R is equal to D, this actually was a code-based paper award by from a few years ago. So compared to this result, we have some technical advantages. Our rates are better and so on. But the most significant issue is that in these results, the sample size goes to infinity as the initialization scale goes to 0, whereas we operate with a fixed sample size, right? So those are some technical comments. There's additional technical benefits that I will not talk about. Then there's kind of the issue of balancedness. So there's a lot of really interesting analysis of this problem in the asymmetric population case when you don't have measurements on top. And a lot of these ideas work based on the idea that the two factors remain balanced. So that's kind of the idea. It turns out that this is not exactly true when you have random measurements on top. So these like in the population case you have balancedness, but in the empirical case, the balancedness is at a much higher level. It actually grows. And so this causes a lot of issues for the analysis, right? So that's kind of one key technical difference. And it turns out that you need finer notional balancedness, which are a little bit technical I'm not going to get into, right? So that's kind of like compared to a lot of work, including by people in audience, that's kind of another challenge that you have to deal with in this case, okay? So I'm going to skip this proof sketch. But maybe, so this is the kind of the sketch of balancedness, right? So that maybe very briefly tell you about the symmetric case, right? Why is it that small random initialization helps? If you look at the first iteration of the gradient, it looks something like this. Now, if you know that you have a small random initialization, you can basically pretend the second term is 0. So if you plug that into the gradient update, you end up with a fixed matrix times u0, right? Now, if you repeat this, right, so in the first few iterations, the size of the matrix is going to be still small. So you can just pretend is a fixed matrix to the power t times u0. And of course, this is nothing but power method, right? Now, why is this matrix a good thing to run power method on? It's because essentially in this case, you can show that it concentrates very well around the underlying planted model, right? So obviously, if I run power method on this, it works very well. Now, in reality, and this is really true in practice, so in reality, this is a little bit more complicated than that. There's actually 3 phases. This is the first phase, which is the spectral alignment phase. There's a second phase where you actually go away from the saddle points, and then finally there's a local convergence phase. So you actually have to do more work, but the spectral alignment phase actually turns out to be very critical, okay? So I'm going to skip this, tell you I'm running out of time. So again, one hidden layer network, come to Jason's talk. So he's going to talk about that extensively. But at the very end, I do want to mention how it connects to end-to-end methods, right? And for that, I'm going to focus on a very simple version of the problem, which is how do I denoise using end-to-end methods, right? And in this case, I selected a subset of the audience and organizers. So here the problem is simple. I have noisy images. I want to train the network to denoise the images, right? And so I'm going to focus on a very simple formulation for denoising, which is I'm going to assume that the signal is actually piecewise linear, and I add Gaussian noise to it, right? So that's the model. The clean data point is piecewise linear. The input is Gaussian noise, and I want to train a network, right? Which goes from the one hidden layer in this case, goes from the noisy images or the signals and figures out the clean image, right? So that's kind of the problem. And of course, I use the least squares loss as with everything else, right? And I run this from small random initialization. So you may ask, what is the effect of large initialization versus small initialization in this case? How does this feature learning manifest itself in this problem? So if you use large initialization, you can see the reconstruction is actually poor. If you use small initialization, actually this is not playing. Okay, can I go back? Okay, so this one is not playing, but you get a perfect reconstruction. You actually get the piecewise linear picture. So in some sense, large initialization is sort of like L2 interpolation. It's kind of like not very good. Small initialization actually perfectly reconstruct a piecewise affine structure. So it's more like a bounded TV norm reconstruction. So that's going to be the key difference here. And I'm not going to talk about the theory, but interestingly, the general strategy is the same. If you look at the training at generalization loss, it has exactly 3 phases again. So there is like 3 phases, as you can see in this plot. There is a first phase where the spectral alignment phenomenon happens, which is basically essentially the parameters, the 2 layers of the network align themselves with the underlying basis of the affine mapping, the piecewise linear mapping. So that's the first phase. There is also like a saddle avoidance phase. And then finally, there is kind of, which is certain minimum eigenvalues, right? The size of the network parameters grow. So that's the saddle avoidance phase. And finally, you get local convergence in the sense that the error actually goes down to 0 at a geometric rate, both in terms of test and train error, right? So interestingly enough, a lot of at least the high-level strategies for low-rank reconstruction carries over to this problem. We haven't figured out the details yet. This is why I had to talk about the low-rank reconstruction problem, but we're getting there. So that's the story. So let me wrap up here. So I talked about kind of 2 different aspects. One was more on the applied side of things, which is like coming up with new architectures for MR reconstruction. Again, this is, on a simple problem, there's a lot of exciting things to come next. And then the second part was focusing on feature learning via gradient descent, right? And the idea was, can we go beyond this sort of lazy training regime? And so there were 2 key ideas. First one was that I want to finish with is that gradient descent has some interesting spectral biases that you could utilize. And there's also a very intricate coupling of the trajectories, right? Even though you have a lot of weights, they kind of couple together in a very interesting ways, which you can exploit to analyze the trajectory, both in terms of optimization and generalization, right? And so I'm going to just end with the papers. So the MR reconstruction paper are out. We have 2 papers on both for low-rank reconstruction in the symmetric case and with Jason on the neural network case. We also have an upcoming paper this month on the asymmetric case and another one also on the signal reconstruction problem. So I'm going to end it here. Thank you.
Hi, thanks for the talk. I have a question about here.
Okay,
The
thank you.
first story. So in the HamasNet architecture, the multi-scale transformer structure seems to be quite flexible. I assume that can also be used to use on other tasks in addition to MR reconstruction, like other low-level vision tasks, such as super resolution and image segmentation. Have you tried this task?
We have not, but that would be very interesting. I mean, we've really focused a lot on MR, and to be honest, our goal of using these models was not to improve the basic MR problem that I talked about. That came as a surprise to us, right? That we could actually improve it even though slightly. Our goal was the other problems that we're working on that I mentioned. So we've been very focused on MR, but that would definitely be very interesting. So I encourage you to try that if that's the area you're working on. Would be very interesting.
Thanks.
Hi. A couple of questions. With respect to the first part of the talk, it seemed to me that, I mean, the wisdom is that transformers require a lot more data than convolution architectures. But your plots were showing that with only 1%, you can do well. So my question is, for those transformer architectures, maybe they were pre-trained on somewhere else. And so the question is whether the comparison is fair in terms of...
So I think, no, well, I agree with you. Transformer models do require more data, but it does seem like when you augment, well, you add like data reduction techniques, like data augmentation or contrastive learning, some of which does require pre-training, right? They work better combined with that, right? And there's some evidence of that in the literature. But you're absolutely right. Just like training a convolutional network versus transformer, obviously transformer require more data, but somehow they couple better with data reduction techniques, such as data augmentation and contrastive learning and so on. So that's the hope, basically.
My second question is about the second part. The scale alpha, I think you showed that you could get much larger step sizes because you had 1 over alpha in the bounds for mu.
Yeah.
But the T also had a 1 over alpha, and so doesn't the number of iterations also go to infinity with alpha going to 0?
Yes. So I think there's a fix to that for that specific case of alpha going to 0, but so it doesn't really have to go to 0. You can cap it off, but I think in some cases, I mean, the dependence should not be log 1 over alpha. It should be max of something and something, but definitely does grow. So this number T should really grow with 1 over alpha, but it should be capped off at some point, which our theory does not do right now. So you're absolutely right. So it captures some aspects of it, but not completely. Yeah.
And my last question is more about debate. So when the neural tendon kernel stuff came out, I was very doubtful. This was several years ago. Primarily because, okay, you've got to stay close to initialization. And so I asked this to Francis Back. And the first thing, it was in the middle of the pandemics, so he said, am I being recorded? And so he admitted. So are you willing to admit that going into the neural tangent kernel direction was a bit of a mistake and led the community towards thinking of a regime that was far from representing the situation where we should be working at?
So that's a good question. I don't think, I mean, I think the community overdid it a little bit, right? But you know, like if you think about it, if 10 years ago, or even 7, 8 years ago, you asked me that we could get global convergence guarantees for the training loss of deep neural networks, I would have been surprised, right? So it is true that it's not in the correct regime, you know, the fine details are not good, but the fact that you can get that with somewhat of an elegant proof, I think is nice. But I do think we, as a community, we overdid it a little bit, right? You know, we focused too much on it, and so that's kind of, you know, trying to deviate from that right now, right? So it captures, like, as with any theoretical result, it captures some aspects of the problem, but in this case, you can see it does not capture more finer aspects like generalization, right?
Yeah, thank you. So I have a comment and a question. So I think on the first question we got from here, it turns out that actually we married fixed match, which is also one of these semi-supervised consistency regularization algorithm, which actually uses augmented data with AST, which is a transformer on audio data, and we got very similar results to yours. In other words, actually it's very robust.
Very good.
So there is something
independent confirmation.
Yeah, so there is something, and it's completely different data, so multi-channel audio data. Yeah. So there's something there, obviously, right? The second question I had is in your first talk. So I've seen some papers using GANs and our diffusers for that reconstruction. So what are your thoughts on that, on how that approach compares with what you're doing?
You're going to get me in trouble a little bit because I'm on record, right? But you know, actually, Reinhard has, this is a lesson I've learned from Reinhard, who is going to talk next in the afternoon, which is basically, it turns out that in practice, right, the GAN approach to solving inverse problems at the moment do not work as well, right? And the issue seems to be basically that, you know, somehow GANs hit an error floor. Basically, you know, like they can reconstruct well up to a certain error floor, but they cannot kind of get past these error floors. And all of the GAN models in the literature, the only thing that changes is the error floor. The error floor keeps going down, so at some point it might be small enough that we're happy with it, but at the moment it's still high. And so that's why if you look at the leaderboard, like the top 10 teams, none of them are GANs. Diffusers, there's not an active result on the leaderboard. So I think that they also share that issue, but there's no verification of that, yeah.
Hey, Mahdi, great talk. I have a quick question regarding the last part of the talk where you gave an example of total variation denoising.
Yeah.
Right. So in that example, and you have 3 phases of learning. So this is clearly not an interpolation regime, right? So do you have the last convergence to the interpolating solution or not? Like if it is interpolating with a noise, then it's clearly not gonna.
Yeah. We don't have exact, right? But you can show you basically, so actually. We actually have a proof for the last phase roughly, or at least the strategy we can show empirically is correct. The strategy is that you actually try to show the TV norm is actually very small, proportional to the statistical min-max error, essentially, right? So that's how we go about showing that, right? But obviously there's some error, but the point is that you know, we can capture there in TV norm, so in some sense it would capture the piecewise affine structure, hopefully, right? But again, you know, like for the last part, there's no concrete end-to-end theorem, so I hate to speculate at this point. I'm just trying to say that the strategy overall seems very similar.
Yeah, in my talk tomorrow, I'll offer a slightly different explanation to how it works.
Okay, perfect. Looking forward to that.
Okay, so I think, well, okay. One.
Okay. You mentioned this puzzle about overparameterization and generalization, but I think in the case of classification under the square laws, as I mentioned this morning, it's pretty clear that you have a lot of degenerate minima, and some are for very large rho, which is the product of the norms of the weight matrices. Those correspond to NTK. They are 0 of the training empirical loss.
Yeah.
But like the standard Rademacher bound show, the ones with larger rho are bad for generalization. So if you have a bias towards small rho, which you can have with even a very small weight decay, or with small initialization, then you get to select among all the degenerate minima of the empirical loss, the ones that are good for generalization.
Yeah, so that's an interesting perspective. Yeah.
And this is, by the way, the standard explanation in the linear case.
Yeah.
You know, you have a pseudo inverse, you have an infinite number of inverses, and what you choose the one with minimum norm, who happen to be.
Of course.
Okay,
and that's why you use small initialization, because it minimizes the distance to initialization. If you use small initialization, it would practically be 0, right?
Exactly. So I don't think there is a big mystery about overparameterization and generalization.
Well, going to the nonlinear case, I think, and especially
the results I mentioned are for the nonlinear case.
Yes, but what we're looking at is the gradient descent dynamics, right? Not just the.
We are also looking at gradient descent dynamics. Actually, there is quite a difference between SGD and gradient descent.
Right.
But that's a separate discussion.
So we can discuss this, but even on the low-rank reconstruction, if you apply any of the existing theory, it would not predict. We've looked at some of those results that you mentioned. It would not predict like this exactly. But maybe we can discuss the details offline. Yeah.
Okay. I probably have one more question, and then we can break up. So I had a question similar to what Rene had, which is with the multi-scale transformer, and you are going to less training data regimes, and there are many methods that now exist in the MRI literature for less training data. And so I was wondering, where does the transformer really fall in the spectrum, all the way to, we have methods with no training data. So, and the other thing was, there's the question of, if you have less and less training data, what kind of theory can we come up with for explaining generalizability with less, in the limit of very little training data? So just what are your thoughts on some of this?
Yeah, so I think that's an interesting question. I don't know if I thought about the first one, which is like, do transformers allow us to bridge the gap all the way to kind of untrained methods, right? I don't know. I mean, it might be interesting. So maybe actually Reinhard might know whether there are untrained methods that are based on transformer networks. How well do they work? So I think that might be a starting point, right? To see if those methods, if transformers also work with untrained schemes, right? So that might be an indication that these architectures are universally better. But I don't know if that has been tried. So I think that's interesting. And sorry, what was the second question?
It's more on trying to understand how methods generalize in the low training data regime.
I see. Yeah. So I think my thinking on that is, well, at least our approach to it would be to try to analyze again gradient descent dynamics for the heuristics that people use, right? But at a higher level, I don't know if I have a better answer than that, right? So that would be my approach, like take data augmentation or something like that, then try to analyze gradient descent dynamics to see what the effect of that is in that. Yeah.
Okay. Thank you. Let's thank Mahdi for this wonderful talk. And